Hello again, and welcome to another episode of Quantum on the Treadmill. Like always, these are questions I ask AI as I try to learn the mysteries of quantum. I hope you enjoy this episode. Thanks again. I'm John Willis, also known as Butcher Galupe. God made the integers. God made the integers. All else is the work of man. It's Leopold Kronecker. It is one of the most famous quotes in the history of mathematics. At first glance, it sounds like a philosophical preference for whole numbers over everything else. In hindsight, it feels almost prophetic. Long before humanity understood atoms, electricity, or computation, we understood how to count. One sheep, two sheep, three sheep. The earliest mathematical artifacts, ancient tally bones carved tens of thousands of years ago, suggest that counting may have been humanity's first abstraction. A notch on a bone no longer represented a specific sheep or spear, it represented the idea of one. That simple leap transformed survival into mathematics. As civilizations emerged, the Sumerians and Egyptians developed formal number systems. Numbers became objects of thought in their own right rather than merely labels attached to physical things. Mathematics had begun. The Pythagoreans took this idea further than anyone before them. They believed that numbers were not merely useful inventions, they were the fabric of reality itself. All is number, they declared. Music, astronomy, geometry, and harmony were expressions of numerical relationships. To them, the universe itself was built from whole numbers and their ratios. Then mathematics suffered its first great crisis. The discovery of irrational numbers shattered the Pythagorean worldview. The diagonal of a square could not be expressed as any ratio of whole numbers. Suddenly, not everything in nature could be counted so neatly. Mathematics turned toward continuity. For the next 2,000 years, continuity dominated scientific thinking. Euclid built geometry upon continuous lines and perfect forms. Newton and Leibniz invented calculus, giving humanity the mathematics of continuous motion. Maxwell's equations described electromagnetic fields flowing smoothly through space. By the end of the 19th century, physics had become a magnificent cathedral built almost entirely upon continuity. Nature appeared infinitely divisible. Then came a glowing piece of metal. In 1900, Max Planck was not trying to reinvent physics. He was trying to explain why hot objects emit the colors they do. Classical physics predicted an absurd result. At higher frequencies, the energy should grow without bound, a contradiction later known as the ultraviolet catastrophe. After exhausting every conventional approach, Planck made an assumption that even he regarded as little more than a mathematical trick. Perhaps energy could not change continuously. Perhaps it came only in discrete packets, one packet, two packets, three packets. For the first time since the ancient philosophers, the integers had returned, not as a human invention for counting objects, but as something nature itself seemed to obey. Planck had reopened a philosophical door that had been closing for more than 2 millennia. 13 years later, Niels Bohr walked through it. Rutherford had already shown that atoms contain tiny nuclei surrounded by electrons. Classical physics predicted those electrons should radiate energy continuously, spiral inward, and destroy every atom in the universe. Clearly, something fundamental was missing. Bohr borrowed Planck's revolutionary insight. If energy comes only in discrete amounts, perhaps atoms themselves possess only discrete states. He proposed that electrons could occupy only certain allowed configurations, labeled not by arbitrary values, but by the same familiar counting numbers. The integers had migrated again from energy itself into the architecture of matter. Bohr's model successfully explained the mysterious spectral lines of hydrogen, something classical physics could not do. It wasn't the final theory, but it pointed unmistakably toward a new way of understanding nature. Then the collision arrived. During the 1920s, classical physics and quantum physics met head on. Newton's universe was continuous, deterministic, and smooth. Quantum mechanics was discrete, probabilistic, and fundamentally different. At first glance, these worlds seemed irreconcilable. Yet Schrödinger and Heisenberg discovered something remarkable. The wave functions of quantum mechanics are continuous mathematical objects, but the solutions they permit are discrete. The mathematics flows continuously, while the observable outcomes appear as distinct quantum states. The ancient tension between arithmetic and geometry, between counting and continuity, had not disappeared. It had become the foundation of modern physics. A century later, that foundation would become the basis of quantum computing. A qubit is not merely a tiny switch. It is a quantum system governed by continuous probability amplitudes that ultimately yields discrete measurement outcomes. Quantum algorithms exploit the continuous evolution of wave functions while extracting discrete information at the end of a computation. In a profound sense, quantum computing is built upon a reconciliation that began thousands of years ago. Ancient humans learned to count sheep. The Pythagoreans imagined a universe built from numbers. Euclid and Newton taught us to describe continuity. Planck discovered that nature counts energy. Bohr discovered that atoms count states. Schrödinger and Heisenberg showed why both continuity and discreteness are essential. And today's quantum computers harness both traditions simultaneously. Perhaps Kronecker's famous remark deserves to be read not merely as philosophy, but as history. God may have made the integers. Humanity spent the next 5,000 years discovering where he hid them.